Hello everybody, my name is Vuko Vukcevic from University of Zagreb, and I'm here to give you a basic programming training in OpenFOAM. Throughout this tutorial we're going to go through adding an additional scalar transport equation to an existing solver, which will include first copying the existing solver or top level application called icoFoam, just renaming it and compiling it to familiarize yourself with the compilation process, and then we're going to add the passive scalar equation along the pressure velocity system in icoFoam, and finally we're going to test it on the most basic test case, which is cavity flow, and hopefully everything will work. So now let's get basically busy. I'm going to use here Foam Extend 3.2, but this tutorial can be followed successfully with any kind of with all kinds of OpenFOAM releases. So the first thing we need to do is source OpenFOAM, and now you probably have your own run directory. So if you do run, you will be inside the run directory. I have some of my stuff here. I just went one directory back, and here you see I have a local installation of Foam and my directory when I put usually my stuff in. And here you have, let's take a look at applications. In applications you have all the binaries, basically executables from your compilation process, something that you have been developing. As you can see, I have quite a few, but that's not really relevant now. What is important is I'm going to put all of my development inside this applications directory, and I'm just going to create a new directory called OpenFOAM 11 training, because this is basically a preparation for the 11th OpenFOAM workshop. There's going to be a training I will give in basic programming, and I wanted to make this tutorial so you can follow it afterwards. So now we have our own directory. We're going to put our stuff here. The first thing, as I said, we're going to do is copy the existing solver in OpenFOAM. You can get to the solvers by typing sol. Now we're in this directory, and and in incompressible icoFoam, this is the solver we are going to use for our further developments. So let me just make a copy of it. Now the good thing, the one thing you need to take into account is it's good practice is you always need to rename your solver, and so I will rename the directory as well, and I will just call it passive scalar icoFoam. And here you have basically three files. The first one is createfields.h. I will go through that one briefly. There's icoFoam.c, that is basically your sort of a main program, which will give you a binary file after compilation. And you see here the dependency files for icoFoam. We're going to remove the dependency files and basically clean the compilation here. So you just type w clean. And also we have a make directory, which sort of guides our compilation process, and in it we have two files, one called files and one called options. Let's take a look what's there in the files, in the file called files. Here basically the first line says what C files you would like to compile, and the second line is where to put the executable, where to put it and how to name it. And we're just going to change icoFoam to passive scalar icoFoam, and here as well the file that we're going to compile is going to be called passive scalar icoFoam, but the application is going to be called the same. Now there's also another important factor, which is a good practice. So you have this environmental variable called foam up bin, and here you see basically the directory where all your binaries are in your OpenFOAM installation. For me it is foam/foam extend 3.2, but you also have foam user appbin, which you should use. This is the one I will show in a moment. So if you do echo foam user appbin, this is basically in my own directory, Vukcevic 3.2, applications, binary, Linux, etc. So now actually let's take a look what's there in this directory. It's a good time to do that. And if you do ls, you will see that I have some of my own top level applications and some of the binaries I've been working with. Now let's get back to important things. So passive scalar icoFoam.c is the file we're going to compile. The name of the binary is passive scalar icoFoam, and we are going to put it in foam user appbin directory, which is this directory. So now we have modified the files. Now we need to see what's there in the options. So in the options you have basically two sort of sets. First is where your include files, that's these .h header files you are going to include in your .c files, where they are. This is where to search for them, in which paths, and you have existing libraries to link during the compilation process. So here we're going to use finite ln include directory in finite volume. Let's take a look at that. So if you do foam fv, you will get to source and finite volume library of the OpenFOAM, which is I think the most used library along the basic foam library. And here you see ln include directory, where you have symbolic links to all the files. So this is where your include files will be searched. And of course you have a basic foam. It's foam or OpenFOAM in the official OpenFOAM release directory, and here you also have an ln include file with these symbolic links, and this foam library you don't need to include it. This one is automatically included for all your applications. So we need to include the finite volume library, and we're going to search for the included files in the finite volume ln include, and the libraries we're going to use is finite volume library and LDU solvers library. So we don't really need to change this file. Now that we have seen what's there in make, and basically change the make files file to adhere to our new compilation, to our new solver, let's just take another look. So now we said we're going to search for a file called passive scalar icoFoam, and we're going to rename our icoFoam.c to passive scalar icoFoam.c. And this is basically the usual process you will use most of the time. You will find an existing code which looks similar to your needs, and then basically copy it, rename it, and add your stuff there. There is no need to sort of reinvent the wheel. And the good thing about doing this is you already have the OpenFOAM programming style inside, so you should, and if you follow that style, your code will look nice, and other people can it will be easier for other people to look through your code. So now let's take a look at passive scalar icoFoam.c, and here you have a general header file, some information about the license, version, and the name of the application. This is just a comment, but it is always good style to update these comments. So this application will be called passive scalar icoFoam. And here is the description. It says transient solver for incompressible laminar flow of Newtonian fluids. And we're going to put with additional passive scalar transport equation, because this is the equation we are going to add. Now, before we go through the passive scalar icoFoam.c, since we have now basically renamed all the files. It's a good practice to just compile it and see whether it works. And you start the compilation of the top level solvers with wmake, which is a wrapper around ordinary make. And let's see what happens. So now it says making dependency list for source file passive scalar icoFoam. So first the dependency list is created, and then the compiler does his job, and then the linker. And here you see we have a few warnings of these unused variables. We will get rid of these in the next release of Foam Extend. I think they're not there in the official OpenFOAM releases, because they have these pimpo controls and piezo controls classes, which are quite very nice. So now let's just check if the compilation process, just to be sure, finished correctly. You can type wmake again, and here it says it is up to date. So now remember that in make files we have specified that we're going to put this application in this executable, binary in foam user appbin. So let's go to foam user appbin here, and here we should be able to find passive scalar icoFoam, and here it is. And as you can see, it's 10:05, and this executable has been created just a minute ago. So now that we have sort of our own application, we need to add our code to it. We're gonna, as I told you, we're gonna add an additional passive scalar transport equation. But before that, let's just take a look at what's inside icoFoam. So before the main program, you have inclusion of fvcfd.h, where you have all the finite volume method and finite volume calculus operators, actually global functions, are declared. And when we start the program, first we're going to have these sort of very common code snippets that we're going to include. So first we're going to set the case, create a time, create a mesh, create fields, and initialize continuity errors. You can search easily for these files using find, for example, in your foam installation. In your foam installation, but we're just going to go through createfields.h in this tutorial, which is sort of included in this top level library. So just to briefly mention, createfields.h defines all the variables we're going to be solving for. So for example, velocity field, pressure field, some kind of probably diffusion coefficients, and for example flux field. We're going to take a deeper look in it in a moment. And here you have a runtime loop, which is controlled by your control dictionary, as you're probably familiar. We reread piezo controls, we check the Courant number, and first we do is create a finite volume vector matrix for the velocity, for the momentum equation. You have ddt, convection, and diffusion, and then you solve ddt convection diffusion equals to minus grad p. And after the momentum predictor step, you have the piezo loop, and it is always a good practice to heavily comment your code. It basically increases readability, and there's a big chance that even if you don't ever open up your code, someone else is going to take a look at it later on, even yourself. So here is just a piezo loop. I won't go through it in detail, but here is how you can see that the FV scalar matrix, how the pressure equation is constructed and solved, and then the flux is corrected, followed by the explicit correction of the velocity. So this is basically our top level solver, and now let's take a look at the createFields.h. First of all, we read the transport properties from the constant folder. We read from the transport properties, we read kinematic viscosity, new. We read pressure, we read velocity, we create a flux, and we set the reference cell for the pressure if necessary. So let's basically start. What we need to do is we need to add a passive scalar transport equation without sources sinks. It's just going to be time derivative, convection, and diffusion terms into the existing solver. So what we would like to be able to simulate is sort of a transient laminar flow, which sort of convects the advects and diffuses the some kind of passive scalar variable. And when I start programming something, in my opinion, it is always a good practice to start sort of from top to bottom. You just go into your top level code and write the code how you would like it to look, and then from that point on you see what variables you are missing, where you need to define them, what functions you are missing, etc. So this is what we're going to do. We're going to go in passive scalar icoFoam, and just after the pressure correction loop where we have conservative fluxes, we're going to add our passive scalar transport equation. So first of all, I'm going to add a comment, passive scalar transport equation, and I'm going to create an FV scalar matrix. It's going to be a scalar equation, psi equation, because I'm going to call my variable psi. Oh, sorry, wrong keyboard. And as I told you, we have DDT, convection, and diffusion operators, and we're going to treat all of them implicitly. So that means we're going to use the functions from the namespace FVM, meaning finite volume method. I will first write the equation and then spend some time explaining FVM and FVC namespaces. So FVM DDT psi plus FVM div plus FVM Laplacian gamma psi. Oh, actually the diffusion term is negative. So this is basically our passive scalar transport equation. We have DDT of psi, convection of psi with the flux, and the diffusion of psi with a diffusion coefficient called gamma psi. So now, as you can see, for example, in pressure equation, I'm jumping a bit back and forth, but I would like to spend some time explaining FVM and FVC namespaces. So, for example, in P equation, you have FVM Laplacian and FVC divergence of flux on the right-hand side. The FVM namespace basically collects the functions, we call them finite volume operators, discretization operators for DDT, convection, and diffusion terms, and basically returns you, given a function, these functions in the FVM namespace return a matrix, return a finite volume matrix which consists of lower, diagonal, and upper parts, and of course the source contributions on the right hand side. In contrast, FVC, all the functions in the FVC namespace return a field. So basically this means give me a flux field which is defined on a surface mesh, and I'm going to give you a volume, self-centered volumetric field by calculating the divergence of that surface field. So FVC functions in the FVC namespace, finite volume calculus namespace, return fields, while functions from FVM namespace return finite volume matrices corresponding to the implicit discretization. So let's now get back to the passive scalar transport equation. Now we have defined it, and we have DDT, convection, and diffusion terms. All of them discretized implicitly, finite volume method namespace. And now we would like to optionally under-relax the equation. You just call psi equation dot relax and then psi equation dot solve. So dot relax will implicitly relax the passive scalar transport equation by looking at the dictionary value in FV solution. You have under relaxation parameters usually put at the bottom of a dictionary, and if you have specified the under relaxation for psi, under relaxation factor for psi equation, this one will be used here. And after the under relaxation we call the public member function called solve, which actually solves the matrix, updates the psi field, and corrects boundary conditions. So this is it basically. With these 10 lines of code we have added the passive scalar transport equation. But now let's take a look what's actually missing. So here this DDT function takes one argument parameter, which is psi, and we didn't define psi anywhere. That's the first one. Phi is completely defined. As you can see here, it is corrected in the pressure correction loop, so we don't need to think about this one. Here again we have psi, and in the Laplacian we don't have the diffusion coefficient for the psi called gamma psi. So the only thing we are missing is volume scalar field psi and dimension scalar gamma psi to successfully simulate, actually first compile and then hopefully simulate our desired physics. So let's go to create fields.h. As you can see here we have one vol scalar field p. Actually it's better first to define the diffusion coefficient because here we have transport properties. We're just going to reuse the code for new. So new is basically has the same dimensions as the gamma psi. So we're going to say dimension scalar gamma psi, look up gamma psi. So this basically defines an object of type dimension scalar called gamma psi, and we're going to create it by looking into a transport properties dictionary. So transport properties is an input-output dictionary, and inside this input-output dictionary you can use the member function lookup to look up something with a given keyword. The keyword is gamma psi and the name of the field is going to be gamma psi. So now we have defined the diffusion coefficient for our passive scalar transport equation, and next we need to add passive scalar which we have called psi. We're just going to copy the pressure because that one is the volume scalar field and put it at the bottom. Reading field psi, vol scalar field psi. We just need to rename these, and let me just go briefly through this constructor. So this is just an info statement for us to see that the field psi is being read, and we're gonna create an object called psi of type volume scalar field, and we're gonna give it an input-output object and a reference to the mesh. The input-output object name is psi. It is sort of a bound to runtime and to mesh. And here we specify whether we must read it or not. And since we are going to solve this equation, we need to specify boundary conditions. We can't just use generic boundary conditions. We will specify here must read, and we will automatically write it, meaning if the write time corresponds to if the current time corresponds to the write time specified in the control dictionary, this field will be automatically written for us. So now I think we have done everything, but maybe I'm wrong. So let's just try and recompile our solver. Okay, it seems everything went fine, but just to check, we're going to do wmake again, and here it says it is up to date. And if you go into foam user appbin, into this directory, and do then do ls-l as we did before, you will see that now it's 10.20 and we have an updated version of passive scalar icoFoam. So hopefully now everything will work, but let's test it, the fun part. So in I'm going to put my actually I'm going to do it more properly. In your run directory, where you have all of these all your current folders, I'm going to create an OpenFOAM 11 training directory. I'm going to go inside, and first thing I'm going to do is copy the cavity test case, because I would like to test it on a cavity test case. Just before we go on, let me explain what I'm going to try to do. I suppose you're all familiar with the cavity. This is the sort of a first tutorial you do in OpenFOAM, where you have 3 walls and the upper wall is moving, and we're just going to put a blob of psi in the middle of the domain and see how it transports. So now let's go to tutorials. You can do it by typing tut, T-U-T, and then go to incompressible, icoFoam, and cavity, and we're going to copy this cavity here. Let's rename it passive scalar cavity. Passive scalar cavity. So I will not go through the foam directory. There are 2 case directories. I hope you're familiar with them, but there's a lot of tutorials you can go to check if you're not feeling comfortable with them yet. So we have 0 constant and system, and what we basically need to do is, first of all, actually let's do it the fun way. We're just gonna create a block mesh and run passive scalar icoFoam, and hopefully the top level solver will tell us what's missing. And as you can see here, it creates time, creates mesh, and then starts reading transport properties. So now if I go to applications, OpenFOAM training, passive scalar icoFoam, in passive scalar icoFoam.c, the create time corresponds to this line of code, create mesh to this line of code, and then we enter create fields. Let's go to create fields.h, and now we have read the transport properties, and the problem happened here because look up in the transport properties dictionary couldn't find an entry called gamma psi. And this is nice because this is actually set here, so it makes your life a bit easier. So if you go into constant transport properties, we're just going to copy the new and call it gamma psi. Gamma psi, and let's say the diffusion coefficient for our psi, let's think of it as an ink. So ink, let's say the ink has a diffusion parameter of 10 to the power of minus 5. So now we have defined the gamma psi. Oh, and just one more note. So here this transport properties dot lookup looks up a keyword called gamma psi and expects a dimension scalar. And this is the keyword that it's looked up. And this is the name of the dimension scalar, because each dimension scalar has a name. These are the dimensions. You have the 7 basic dimensions. These are exponents. And here you have the value for the scalar. If it was a vector, then you would have 3 values. But this is why you have sort of a 2 names. The first one is the keyword looked up, and the second one is the name for a dimension scalar. Now let's try to run the passive scalar transport, passive scalar icoFoam again, and now it read transport properties, read P, read U, and was stuck at reading the field psi. Why? Because we need to define it in our 0 directory. So in 0 we have P and U, and since P is a scalar, we're just going to copy it and call it psi. Oh, sorry. Let's change the name of the object. And our psi is, since it is ink, let's say it's dimensionless. Sort of a ink is, this is an indicator field for, this will be an indicator field for the ink. If ink is 1, if the psi is 1, we have 100% of ink, and if psi is 0, we have 0% of ink. And we have these boundary conditions. Here you have internal field, which is 0 everywhere, and the boundary conditions will be 0 gradient everywhere as well. Okay, now we have successfully read psi. We have gone through the pressure velocity coupling. You see here the momentum predictor step was finished, and then the pressure was corrected twice, and then we experienced the error because we are missing Laplacian gamma psi discretization scheme, and this happened in here basically, because the Laplacian operator expects the keyword which will guide the discretization process during runtime of using gamma psi and psi. So let's go into FV schemes, and in FV schemes we have a subdictionary called Laplacian schemes. We're going to copy the, for example, Laplacian scheme for new, Laplacian scheme for new and u. Actually, let's break the line. It's called, we're looking for the Laplacian scheme for psi, with the diffusion coefficient called gamma psi, and we're going to use Gauss linear corrected scheme. So now I would also like to add the convection scheme, because this one will still complain. We need the div scheme. Div phi psi, and let's use upwind difference. And now we also have a DDT scheme, but actually we don't need to specify it, because here the default scheme for all the DDT terms is specified. So we're going to use Euler. So now I think that's it regarding input, but we still initialize the psi with 0 everywhere, so we will have basically nothing to solve. What I would like to do is put a blob of ink in paraview, but let me first just briefly open paraview. Oh, I can't because I'm not connected to the X server. Okay, give me a second. Okay, now let's take a look at paraview. So basically this is your cavity test case. You have a really small and coarse mesh, and this wall is moving in positive x direction, and these are fixed walls. And what I would like to do is put a sort of a blob of ink where psi will be equal 1 in sort of a middle of the domain. Now let me just go back, and now we're gonna use the set fields utility, but let's go into tutorials and I'm just gonna try and find set fields set fields dictionary, and let's say we will take the one from the dam break, which is again one of the usual two-phase flow tutorials, and I'm just gonna copy it here for the moment. So set fields dictionary, and now let's see set fields dictionary. So here you set up the default field values, and then in regions you set up different values, and our field is now psi, not alpha 1, and default will be 0, and here psi in our blob in the middle will be 1. But I forgot to check the extents of the mesh, so if I run check mesh, the bounding box is in the x and y direction 0.1, and z direction is basically dummy. This is a 2D test case. And now let's put the blob in the middle. We're going to use sphere to cell, and we define the sphere by center and radius, if I recall correctly, and the center is going to be in 0.05, 0.05, and let's say 0, and radius is we'll put the radius of 0.03, for example. We just delete this for a box, and inside in the sphere defined by a center and the radius, we will put wall scalar field psi values to 1. Now let's do set fields. Now let's take a look at it in paraview. So if I color psi, I get a blob of ink in the middle of domain. There psi is 1 and 0 elsewhere. Now we're gonna run the simulation, but before we run the simulation, we're gonna put end time to 2 seconds to see what happens, and now hopefully our simulation will work. And of course it doesn't work because I forgot to define a solver for the psi, because in let me show you. So applications, OpenFOAM workshop training, passive scalar icoFoam, passive scalar icoFoam.c. So in psi equation.solve, this one actually searches a finite volume solution dictionary, to be specific solvers sub dictionary in it for psi. Basically this defines how you will solve the linear system, and we're just gonna copy the one for the velocity, because the equations have the similar nature, both of them are parabolic. So we're going to use precondition by conjugate gradient with ILU without fill-in, preconditioner ILU without fill-in, and with these tolerances, and we won't use any under relaxation factors. So now the simulation is running, and as you can see in one of the time steps, we have first momentum predictor step, pressure correction, 2 pressure correction steps, and then we solve for our passive scalar. And now we ran up to 2 seconds, and let's take a look in what happens in paraview. So this is our initial condition, and as we go through the time, the ink, which is initially a blob in the middle, slowly starts convecting and diffusing because of the moving wall boundary condition. And at the end, at 2 seconds actually, this is how our field looks like. So this ends our first tutorial, and I hope this was interesting, and stay tuned for more. I hope there will be more videos like this in future. Thanks for listening and watching.